Hello, everyone. This is Randall Pike speaking. I'm going to lecture on section 3.2, matrix mappings and linear mappings. So let's go. Now, we have some terminology, as we typically do in this course, each section. I'm just going to highlight some of the terms that are similar, so synonyms. So you know what a function is. So it's a rule that assigns from an input, it gives you an output. The inputs lie in the domain, the outputs lie in the codomain. Now, in linear algebra, we often use the term maps or mappings. So that's a synonym for function, okay? You will see in this course. We also mention the image, which is the output of a function. That is from a particular input. It gives an output. The output we call the image of the input. Pre-image is where you start. Mapping is this other synonym for a function that we use, map or mapping. So that's another one here. We also use the term transformation. That's another type, another word we use for a function. Except here we're usually restricted to the vector spaces Rn and those. And what we're going to talk about in this section here are special kinds of functions called linear functions or linear mappings. Okay, so there's the two terms at the bottom. And really that's the subject matter of linear algebra is the linear transformations. So these will be particular types of functions from Rn to Rm. So moving vectors from one space Rn to another space Rm. This is the main subject matter of linear algebra. So let's start with something we're familiar with. You've learned how to work with matrices and their operations amongst themselves and also on vectors. So we can use them to define a particular function from Rn to Rm. So we have a matrix here. All right, so this matrix here would have to be size according to what we have here, m by n. And remember, m is the number of rows, is number of rows in the matrix, and n is the number of columns. All right, so what we're saying here is if you have such a matrix, then it defines a mapping from Rn to Rm. That is, the input are n-dimensional functions, vectors, and the output are m-dimensional vectors. So for example, here, we see A is 4 by 2. So this F maps from, you start with vectors in R2, and you end up with a vector in R4. Okay, so, and that's determined by the matrix A. So you can see from the example here that it's taking vectors in 2 dimensions, but we'll see the output is going to be a vector in 4 dimensions. So let's compute this according to our definition. So f of A acting on a vector. So let's write the vector in horizontal mode is matrix multiplication. So I'll just write out the matrix once here, and then I'll use A later on. All right, so I'm going to multiply this vector by, or this matrix, let me write it vertically now, by this vector here. So we do the matrix multiplication. Okay, so I'll just do it once here. So it's row dotted with the column there. So I see -4, -15 for my first entry. Then I go to the second row, the 3, 0 row, which I'll start to highlight these. So I did the first row, now I'll go to the second row, and I dot it with the column there, and I get 6 by itself. And then I go to the third row, and I'll dot it with that column, and I'll get 2 minus 25. And then the bottom row, now dotted with that column vector, is going to be 8 plus 30. Okay, so I did the details there, and then I'll just simplify a little bit. So I get -19 minus 23, and then 38. So I'm doing this basically as I write. So you guys will check the algebra. And then let's do the other one. So now FA acting on, I can shorten my calculations. This is going to be A acting on the vector minus 3, 4. And if you do that calculation, you're going to see you'll get 18 minus 9, 17, 36. So in these examples, we'd say F takes the vector 2 minus 5 to the vector minus 19, 6, minus 23, 38. So this is the image. So we'd say F maps 2 minus 5 to this vector minus 19, 6, minus 23, 38. And we'd also say that this vector here, minus 19, 6, minus 23, 38, is the image of the vector we started with, which is the input, the pre-image, image of this vector under this function fa. Okay, so some use of that terminology. F is a mapping from Rn to Rm. The image of 2 minus 5 is this vector minus 19, 6, minus 23, 38. The pre-image of this vector minus 19, 6, minus 23, 38. The pre-image of that is the vector 2 and minus 5. And the image of 2 and minus 5 under this function f is that vector minus 19, 6, minus 23, 38. Okay, so let's look at other particular images of particular vectors. So we're going to talk about the standard basis vectors, and this is going to really simplify our calculations. So let's compute f of a acting on E1. Okay, so F's domain is R2, so this is going to be the standard basis is E1 and E2. So let's compute that. So this is going to be A acting on E1. Okay, so it's A acting on 1, 0. And if you do that multiplication, you're going to see that because there's a 0 in the second component, you're just going to pull out the first column of A. Okay, so it's the first column of A. And you'll see that if you take the image of the second standard basis under this F, it's A times this vector, sorry, 0, 1 now. And you'll see because there's a 0 in the first entry, when you do the matrix multiplication, you're going to get the second column of A. So this is an important observation. The standard bases are picking out, and you've seen this in the textbook, are picking out columns of the matrix A. Okay, so that's important. So first and second columns of A. Okay, when you multiply or when you apply the function f, matrix multiplication, this matrix mapping to the standard bases, the outputs are going to be the columns of the matrix. Okay. So now we can write out, this is going to be a good formula for us, FA on an arbitrary vector. So f of A acting on x1, x2. So there's the components of my vector x and R2. Okay, so I have my matrix, minus 2, 3, 3, 0. I'm going to write it out. Yes, let's do it this way then. 1, 5, 4 minus 6. Okay, so x1, x2. And then I write this out, the dot product, row dotted with the column there. So minus 2x1 plus 3x2, 3x1, and then x1 plus 5x2. And the last component would be 4x1 minus 6x2. Now I'm going to rewrite this. I'm going to factor out this number x1. And I see it's multiplying against the first column of A, and then I'll factor out the x2 from this expression. So I get the sum of these two vectors. This is a linear combination of vectors, and the vectors it's a linear combination of is exactly the columns of A. So I want to point this out here. Okay, something to make note of. So this product FA, so X, or the image of FAX, which is this matrix product A times X, is a linear combination of the columns of A. And this is going to be useful later on, this interpretation of A. And the coefficients are the components of that vector A. With coefficients, remember, a linear combination of vectors is a sum of vectors that have coefficients multiplying them. And these coefficients are the components of the vector A, with coefficients that are components of A. So we can interpret matrix multiplying on a vector as that particular linear combination. Okay, so that's just a note here. We recognize that. Okay, so that's a particular function, a particular mapping from Rn to Rm we created once we're given a matrix. Okay, so if you're given a matrix, this one here in blue, oops, in blue, right? This one here. If you're given a matrix A, then that defines this mapping F sub A. And you can tell what the Rn and Rm are from the dimensions of A. You start in the dimension that is the number of columns of A, because that's the way matrix multiplication works. And you end up in the dimension that is the number of rows corresponding to the number of rows of A, because that's also determined by the way we do matrix multiplication. Okay. Now let's talk more abstractly about particular kinds of functions, linear mappings. Okay. So here's a definition, another definition for you. We're using the symbol phi. Okay, so phi is going to be denoting a mapping. So remember, it goes from Rn to Rm. And it has this property here. So there's this linearity with respect to scalar product. So linearity, linear with respect to scalar product. So there's my scalar product right here. I'll just circle it in yellow. Okay, k times x. The k comes out. Okay, so on the left of that equation I'm looking at there, I have scalar multiplying the x, but on the right I have the scalar multiplying this other vector in Rm, which is phi x. It's in Rm. On the left, the vector is in Rn. Okay, so this k can be pulled out. And now on the right term there, we call that linear with respect to vector addition. So this is a property of phi, vector addition. So when I look at that expression here, this one, I see that on the left I have phi acting on a linear sum of x and y, and on the right I have the sum of the two vectors phi x and phi y. Notice the vectors x, y on the left, which are added on the left, they're in Rn, whereas the vectors that I'm adding on the right are in Rm. Okay, so the addition can be done either before or after you've computed phi x and phi y. I mean, if you do it before, that means you're going to act, you're going to apply phi to the sum x plus y. Or if you want to do it afterwards, it means you're going to compute phi x and phi y and then do the sum. Okay, so that's a very particular property of a function that maps from Rn to Rm. Very particular. If you just generally pick a function from Rn to Rm, it won't satisfy this. But this is the topic of linear algebra, these types of functions. These are called linear mappings. And we're going to have a lot to say about these ones. So in particular, we can show that, if I could open this up without ruining it. Okay. That kind of ruins it. Anyways, I'm going to just erase those things. I'm going to show that matrix mappings are linear functions. So matrix mappings, the ones we just talked about before, okay, just above here, are linear mappings. And that's a property of matrix multiplication. So it won't take us hard to prove this. Okay, so we have f of a. I'm going to prove the scalar multiplication. Okay, so that's what we start with, k times x. So whatever size a is, I don't need to specify, but x would be the appropriate size according to the matrix A. So here we apply the definition of what this symbol f sub a means. It means it's matrix A acting on the vector kx. Now you've seen that matrix multiplication is also linear under scalar multiplication. So this, according to the rules of matrix multiplication, this is k times ax. Okay, k times ax. So we have by matrix multiplication, and also we have this product here. If I have two vectors, so these are the vectors, x and y. According to the definition of f sub a, this is going to be ax plus y, a acting on x plus y. And because matrix multiplication is linear, this turns out to be ax plus ay. All right, so linear mappings, matrix mappings are an example of linear mappings. What we're going to see down below is the remarkable fact that all linear mappings, all linear functions from Rn to Rm are in fact matrix mappings. There's a certain matrix that defines it, and that's what we're going to learn below here. So it's going to be very important for us to recognize such types of mappings, that is linear mappings. So here's some examples to work on. So it's a definition, two properties of a linear mapping. If it satisfies these two properties, then it is a linear mapping. So we have to verify these two properties when we're given a function. So there's many ways to define a function. So in these two cases here, the output is given as a vector, as a formula in the components of the inputs. Okay, so that's one way to define a function. So let's start with the first one. So L, this L here, is a function, first of all, a mapping from what dimension to what dimension. So I'm looking at the inputs. The argument is x1, x2, x3. So that's three components. So it starts with a vector in R3. And it ends up with, if you look closely, there's just one comma there, 2x1 comma, x1 minus x2 plus 3x3. So it goes into R2. All right, so that's from looking at the formula that was given to us. So let's prove that this L, or let's determine whether it is. So I'm going to look at this formula here. I'm going to make a note here that the equivalent way to do this, and this is how it's defined in the book. Equivalently, we say that a mapping is linear if phi acting on tx plus sy. Okay, so there's a linear combination of vectors. You end up with a linear combination of the outputs, the same linear combination. So in other words, t times 5x plus s times phi of y. Okay, so that's the way the textbook defines linearity. And you can do it either way. You can do it in one step, which is this, or you can do it in two steps, which is linear with respect to scalar product and linear with the vector addition. I can see that the equivalent one is it's equivalent because if I take t and s to be both 1 in that formula, then I get the second one, the linear with respect to vector addition. And if I take s to be 0, then I'll get the linear with respect to the scalar product. Okay, so they're equivalent. And I'm going to use this second version to do it because the textbook also uses this second equivalent statement of linear mapping. So let's do it this way. So if I want to show that L satisfies this property here, I'm obliged to start off with this type of linear combination. So t times x plus s times y. So ts scalars, x, y are two vectors in R3. And away I go. And I want to end up with so I need to show, I'll just do it here, because sometimes it helps when you do proofs to know where you're ending up so you can kind of apply the right steps to take you there. So I need to show, I mean, our goal is to show this is a linear mapping, if we can do it. And if we can do it, then we need to show that this initial quantity right here, this one here, should end up to be, according to the definition on the right there, t times L acting on x plus s times L acting on y. Okay, so that's what I need to show. That's where I'm headed. So as I go through these steps, I'm guided by that form I want to find. So here we go. So I start with that. I'm obliged to start with this vector, tx plus sy, because that's the definition. Now I have to use the properties of this L. Okay, first of all, let's do the vector addition. All right, so this is going to be the vector tx1, tx2, tx3. Okay, so there's my scalar multiplication, and I'm going to do the scalar multiplication on y. So it's s1y1 plus s2y2 plus s3y3. All right, so I've done the scalar multiplication. Now I'm going to do the vector addition. Okay, so I have these two vectors in R3 inside the brackets, and I'm adding them. Okay, now we know how to add vectors. When we see the components, we add the components. So my first component of the vector on the inside is going to be tx1 plus sy1. Okay, and the second component is going to be tx2 plus sy2. Okay, and the third component is going to be tx3 plus sy3, and I shouldn't be writing those sub-indices under the s's because it's the same s's. Okay, so it's just, yeah, that's right, there's no 1 there. So s times y1, s times y2, s times y3, same with the t's. Looks good. Okay, so I've done the vector algebra, okay, on the input. Okay, now I'm going to use the definition of my L. So I go back to my L and I see the output. I'm going to do it in red. The output first component. So this is a vector in R2. So I'm going to write now down my vector in R2 here. The output of this L on this vector is 2 times the first component of whatever is the input. So 2 times the first component, and I see it here. It's tx1 plus sy1. Okay, so I'm done there. Then I move on to the second component, and I look at my formula up here. That's this part. I see it's the first component minus the second component plus 3 times the third component. That's how I'm reading it, because the x's you see in this formula up here are not the same as you see down here. Okay, I'm referring to the components of the vector that was the input. Okay, so I'm going to read it that way. So the second component of the output is going to be the first component, right? So I'm going to write that out, and I see it's so tx1 plus sy1. There's my first component minus the second component, which I see is tx2 plus sy2, all right? Plus 3 times the third component, so 3 times tx3 plus sy3. All right, so I've applied the definition of L here. So I'm basically done. Now I look at where I want to go. Okay, I want to get that expression here. And you see that I need to get the t factored out and the s factored out if I can. All right, so I look at this expression here. So I don't need these brackets on the outside anymore. So that's that. All right, so I just have this, sorry. I guess I do. So that's my vector. So I want to rewrite this vector as a sum of two vectors, one which has a component of t and one which has a coefficient of s. Okay, so so let's do that multiplication here. So I get 2 times tx1 plus 2 times sy1, okay? And then I'm going to get this term here. So this is going to be my tx1. So I'm going to combine my t's together. You see that? So I'm just rewriting the order here, and then I get my sy1 minus sy2 plus 3sy3. All right. So I just rewrote the order of the components on the second there. And now I'm going to split this up in two vectors, one which has a coefficient of t, and I see that vector is going to be 2x1, comma, x1 minus x2 plus 3x3. All right. And then I get another vector here, which has a factor s, and I see its first component would be 2y1, and its second component is going to be y1 minus y2 plus 3y3. Okay, so now I've written this vector right here as a sum of two vectors, as a linear combination. And I was guided by, again, this output here. This is what I'm aiming for to finish the proof. I want to get two vectors, one which are linear combinations with the coefficients t and s. So that's why I was striving to factor out the t and factor out the s. And of course, we're not finished yet. So now I recognize this as indeed t acting on x1, x2, x3, isn't it? According to our formula up there, that's exactly what it is. And then the second vector can be written as s acting on the vector L of y1, y2, y3, according to the formula up there. Sorry, am I missing a 2? I'm missing a 2 there, and I'm missing a, sorry, I'm not missing a 2 there. That's just the way it turns out. Good. So we're done. Okay, so this is where we wanted to go. So TLX and SLY. Okay, so that's a proof. So the first one is linear. Now, the second one, I want to point out this fact. For any linear mapping phi, okay, phi of the zero vector must be the zero vector. Okay, so it takes the zero vector to the zero vector. And the proof is simply this. Phi times k, phi times, k times 0, right? Phi times k times 0 is going to be k times phi of 0. Is this what I want to write? I think so. So it has to be 0 because actually I should do it this way. So times x, okay? So hopefully this is going to be that. And so when k is 0, k equals 0, this side is the 0 vector, okay? So that means this would be the 0 vector then, okay? So because of the scalar linearity, when I act on a vector x and I multiply by the scalar 0, k times x, 0 times x is 0, phi necessarily takes that 0 vector to the 0 vector, okay? And the reason I put this here is because this second function up here, this g of 0 is equal to, if you look at it, it's always equal to 1, 1, 1. Therefore, it's not linear because a linear mapping necessarily must take 0 to 0. Okay. You can also see, just for educational purposes, also see this because if I take g acting on a sum of x plus y, I don't get g of x plus g of y. Okay, I don't get that. And the reason is because this is going to be 1, 1, 1 plus 1, 1, 1, which is 2, 2, 2. Whereas this one is always going to be, whatever input you have, you get 1, 1, 1. Okay, so that's another way to see that it's not linear. It doesn't satisfy the sum property. Okay, so there's two ways to prove that the second function isn't. And we're going to, and I'm going to make a point here because it's so important for us to recognize when a mapping is linear or not, because many of the theorems, all the theorems that we deal with in linear algebra, all the applications require the functions to be linear. So note that if fx1 is linear, then the output vector, so that's on the right hand side, has components that are homogeneous linear terms in the xi. Okay, so if you have a formula like up here, this formula for L there, this one here, see on the right, I have a vector whose components are formulas that depend on the input variables. So I just look at the vector on the right. If I see if it's given to you this way, so formulas for each component, then those formulas must be homogeneous linear terms. So homogeneous means that there's no constant term. Homogeneous linear, so no constant. Like that G, the second one, had constants 1 in all components, but if it was just a constant 1 in just a single component, but not in the others, it would still not be linear. So no constant terms. That's what homogeneous means. And linear means power of 1 there. Okay, so for example, g, x1, x2, x3, even if one component was just a constant like 1 and then x1 plus x2, so the two second components are linear homogeneous terms, but the first one is not. Okay, so this is not linear. So you don't need all the components to be constant. Just one of them would ruin it. Okay, so there's most formulas you're going to write out in this form will not be linear. So they're very special forms. So what we've seen up above is many examples of linear mappings. Okay, because we showed that up here. Okay, we showed that matrix mappings are linear mappings. Okay, so this is what I'm referring to. So although linear mappings are very rare in a sense, because the formulas have to be a very special form, these types that are given by matrices via matrix multiplication, they are linear mappings. Okay, so there's a whole bunch of linear mappings at our disposal right here. You pick an A, and then you have a associated linear mapping. Turns out, and this is a remarkable fact down here, it turns out that all linear mappings are of this form. That's all of them. Okay, there's no other kinds. So there, and that's something we need to prove. Very important fact right here. Okay, so let me say something about that proof. This is a theorem in the book. So this is a theorem. You can look at it there, but let's go through it here. All right. So we have proof is the following. So what I want to do is, so there's two things to do. This is an if and only if. Okay, so let's do the only if. So if L is a matrix mapping. Okay, that's what we talked about above. So i.e. L acting on X is given by a certain matrix multiplying by X. Then I've shown above, then it is a linear mapping. Okay, so that's that. I did that part there. Now the other one is more work. Okay, so conversely, suppose L is a linear mapping. Let's find that matrix. We have to do that. Okay, so what is the matrix for it? That's the question. Okay, so it's not hard to do, but let's pay attention here because it's a very good calculation. So let's take L. So it's a mapping from Rn to Rm. That's all I know so far, and it's linear. Okay, so what is the matrix? That's the question. So let's take an X in Rn. Now here you're going to see the utility of the standard bases. So I can write X as a linear combination of the standard bases. All right. So x1 to xn are the components of my vector, and those are the standard basis vectors, e1 to en. Good. So that's my first crucial step, and then I look at L acting on this x. So my goal here, okay, I'll just put it on the side again, because once again, you know, proofs, if you know where you want to go, then that can act as a guide. So the goal is to show that L acting on x is matrix time, some matrix times x. That's our goal, right? Because we want to show that this L, this arbitrary linear mapping, is actually a matrix mapping. So I need to exhibit that matrix A. That's kind of the hard part about this proof. You know, where are you going to get this A? You have to create it, you know, from just what you know of L. So here we go. So the first step was to write x as this linear combination. Okay, so that's in the standard basis. Now so L of x, now I'm going to write it this way. So instead of x vector, I'm going to write it this linear combination. Okay, fair enough. Now I borrow the properties, I use the properties of this vector, of the linearity of this L, this mapping L. So now that's a sum, okay? Now it's not hard to show that. Linearity, if L is a linear mapping, then it's linear across multiple sums. So I can break this up into each term separately. Okay, so that's a good exercise for you. So this is what I mean. So although the definition of linearity had L acting on x plus y, only two vectors, you can have any number of sums of vectors, and L will break it apart this way. So each one, and that's an x2 there, can be taken out into a separate term. Okay, so you see that sum inside of n vectors became a sum outside of n vectors. So the plus signs became out on the outside, and they're sums now in Rm. Okay, so the first line here, this is a sum of vectors in Rn, but on this line, that's a sum of vectors in Rm using the linearity of L under vector addition. Okay, in the extended sense. So there's a sum of n vectors here, more than two, say. This is still correct, and you can show that using the property of linearity. You do it pairwise, one at a time, until you break it all apart. Okay, so now I'm going to use the second property of linearity of L, and that is the scalar multiplication. These x's are scalars. Okay, so now I take them outside, so I get L acting on E1 plus times x1, and then x2 acting times L acting on E2. Okay, so I'm just writing down I'm just using L here, its properties, as far as I can go, because we're trying to prove that a function with these properties has a certain matrix associated to it. So you would expect that you need to use those properties to reach the end of the proof. Okay, so now I've used them. Okay, so now I've used this linearity under scalar multiplication. So there's not much more I can do because I don't know anything else about this L, but let's see what we have. We have, and I've mentioned this just above there, right? This is a vector, these are vectors in Rm, and I have them multiplied by these scalars. Okay, so this is a linear combination of vectors L EI, those vectors. All right. Now, if you go back, I'll just go back and highlight it here. I mentioned, and here I noticed this is a bit messy. I can move this around. So I'm going to put this back to where it belongs, which is up here. Right. Good. So very important fact here. Okay, where was it? Sorry, there it is. Maybe I'll put it in red now. Okay, so it was worth, and this was mentioned in the textbook when they talked about matrix multiplication. So this product AX here, this is what I'm highlighting. When I have matrix multiplication, the answer is a linear combination of the columns of A, and the particular coefficients are the components of that X. I'm going to go backwards down here. Okay, so I do have a linear combination of vectors. I'm going to interpret those vectors as components of a matrix. Okay, so this turns out to be a certain matrix, which we denote by box L, acting on the matrix, the vector X, where L square, or box L, is the standard matrix. All right, so I'm defining what it is of L. All right, so there's my definition, and we see what it is. So L is the matrix whose columns are the vectors you get when you act on the standard bases with the L. Okay, so first column would be L, the vector L acting on E1. The second column would be the vector L acting on E2, and all the way to the n. So L acting on En. Okay, so it has n columns and m rows. Okay, so there it is. There's our matrix A that I was searching for. There it is. Okay, so we're done. Proof is done. So the proof is a constructive proof. If you're given such an L, a linear mapping, this is the way you find that matrix A. So now we can realize it as simply matrix multiplication. Okay, so there's no other linear mappings than these types. Okay, so back in familiar territory, dealing with matrix multiplication. So all our linear transformations, our linear mappings, our linear functions are simply going to be matrix multiplication, matrix multiplying vectors. Okay, so let's work on some examples of finding the standard matrix. Okay, so now we're going to look at an example we're familiar with, projection. And we're going to do projection onto this vector. Okay, so projection in R2. So this is going to be a linear, what we're going to show, it's a linear function from R2 to R2. Okay, so this kind of projection along a vector in R2 is a function from R2 to R2. You start with a vector in R2 and you end up with a vector in R2. Okay, so I miss that piece, should be somewhere else. Yeah, I'm gonna just, I don't want to move it yet. This little piece here, I notice should go right here, right? It's the example there. Okay, it's too late for me to move that. So first of all, let's prove that on the side here. Let's show that, first of all, projection and perp, they're both linear functions. So projection, V, and perp, V, are linear mappings. Okay, so here we go. Let's show, I'll show it for projection, first of all. Okay, so then once we've established a function is a linear mapping, then we can find a matrix. If a function is not a linear mapping, this is for you to think about. If it turns out not to be a linear mapping, you can still compute this matrix here, this box L. You can still compute that. If L is not a linear mapping, you can still compute L of E1, L of E2, L of En, okay? Form that matrix. My question to you is, what use is that matrix? What does that matrix tell us about that nonlinear function? Think about that, okay? The answer is it doesn't define the function, all right? So here, this is what I'm getting at, because when we want to compute the standard matrix of a transformation of a mapping of a function, I can always compute that matrix, but unless the function is a linear transformation, a linear mapping, that matrix won't have anything to do with the actual function. Okay, it's only when the function is linear. Okay, so that's why I'm establishing over here, first of all, that these two mappings, projection and proj and perp, are linear mappings from the way we've defined them previously. So let's go. So projection, if you remember what that is, and here it doesn't matter the dimension. So projection onto V, all right? So this is in any dimension. So V is in Rn. So let's take a linear sum of two vectors. Now remember the formula for this. It is the input vector dotted with the V divided by the norm of V squared times the vector V. That's the formula for the projection. Okay, so let's continue on. So now I use the linearity of the dot product. So this is x dot V, okay, plus y dot V. Okay, so I distributed the dot product over the sum divided by V squared times V, fine, property of dot product. And now I'm going to split that into two. So this is a number multiplying this vector V, but it's a sum of two numbers. So I have one number, which is x dot V over norm V squared. Okay, so that number is multiplying again onto V. And then the second number is y dot V divided by V squared acting on V. And now I see this is project onto Vx plus project onto Vy. See? Okay, so I proved the linearity under vector addition. And then also you can show that project V of Kx, right, using the properties of the dot product, is K times project V of X. And similarly for perp, okay, because the perp formula is just X minus the projection. Okay, so you can do that one. Similarly for perp. All right. Okay. So I don't have to write the argument here. I mean the perp function. Good. So all right. So that's the aside that convinces me that these are linear functions. So they do. So the matrix I compute according to the formula above, this one right here. Okay, I'll put it in yellow now. This is our important formula to remember, right? Red star. Okay, this is the definition of the standard matrix. It allows us to determine a function by matrix multiplication. So we can use this matrix to determine anything we want about this function L. So this is what we're trying to compute here. Okay, so I'm going to compute it, the two matrices. So let's do that now then. So so L. So I have to compute. I have to compute the standard matrix. So I have to do the projection of that. So I'm going to call that L, and I'm going to call that M. Okay, so I'm going to look for box L and box M. All right. So I need to compute L acting on E1. Okay. So L, I should write it down here as a reference on the top. Okay, so let's just keep it here. So L acting on X is projection V of X, which is equal to X dot V, norm of V squared, V. Good. So L acting on E1, according to this formula, is going to be E1. Okay, so let's write it out here. So it's minus 2x1. That is our vector V, right? Minus 2 and 1 So x being x1, x2, I'm going to get the dot product to be minus 2x1 plus x2, and the norm squared of v is 5, and then multiplied by v. Okay, so that's our formula. So now when I look at E1, which is x1, 1 and x2, 0, I look at that formula and I get minus 2/5 minus 2, 1. Okay, and then if I look at E2, the standard bases, E2 is components 0, 1. So x1 is 0, but x2 is 1. So I see 1/5 times minus 2, 1. And therefore, I form the matrix. So this is the standard matrix of L, which is the projection onto V, with 2 columns. It's from R2 to R2, so it has 2 columns. The first column is LE1. So I'm just going to write that out here. So it's 4/5 and then minus 2/5. So that's the vector LE1 as a column. The second column of box L is the vector LE2 written as a column vector. So minus 2/5 over 1/5. Okay, so there it is. That is the operator, the standard matrix of L. So let's check. So what is L acting on our vector? Yeah, so let's do it now. So, well, let's do the perp first, I guess. All right, so now we do the perp. So M equals perp M of X. Let's write out the formula so we remember what it is, right? So M acting on an X, this is the perp part, equals perp. Remember that's X minus projection of V of X, all right? So it's going to be so I can see that vector up there. So it's x1, x2 minus this one, minus 2x1 plus x2 over 5. This is what I have to refer to now when I compute the columns of the standard matrix for M, which will be M acting on E1. So now I look at that formula I just finished writing, and I think of the x vector being my E1, okay? So when it's E1, that means x1 is 1 and x2 is 0. So I'll get my, I'm going to write out my first vector there. But because I have this fraction, these fractions with 5 on the bottom, I'm going to write it like this. Right? So there's my E1, right? That's the vector 1, 0. And then on the second term, which I'm subtracting, is going to be, when I factor out that 1/5 also, is going to be 4. Sorry, 4 and minus 2, right? And so when I do that, I get 1/5 and 2/5. All right. So that's my PE1. So that's going to be my first column. And then M acting on E2, I look at that formula. So first of all, I'll write E2 as 0, 5 multiplied by 1/5. And then I get minus 1/5 minus 2 and 1. That way, right? I take out the 5. And then doing the algebra there, I'll get 2 over 5 and 4 over 5. Okay, so the standard matrix for the perp part, box M, is going to be first column is M acting on E1, so 1/5, 2/5, and then the second column is the vector M acting on, or the vector ME2, which is 2, 5, and 4, 5, 4/5. All right, so there's my two standard matrices for those 2 linear transformations. So I'm going to use them now, as the question asks, to compute the projection. So we're going to do it 2 ways just to test, right? So projection onto V of this particular vector, 1, 3, is going to be given by the standard matrix of that linear function acting on the vector 1, 3. Okay, so I'm going to do it that way. So when you do that calculation with that L above, we get minus 2/5. You can check 1/5. Okay, so that's the matrix multiplication. So there's my box L up here, right? So I'm going to do that matrix multiplication. You guys do that. This is what you get. And then the perp one, perp V of 1, 3 is going to be obtained by matrix multiplication with the standard matrix for perp, which is the M. I just finished. And when you do that calculation, you're going to get 7/5, 14/5. Okay, so this one using our standard matrix for M, which is this one up here. Okay, so there it is. Now let's just confirm with our formulas previously. So our formulas previously told us, that is previous lecture, so projection onto V of 1/3 is going to be that dot product. So V dot 1, 3, not 1/3, but 1, 3 over the norm of V squared, which is 5, times V, which is minus 2, 1. And the dot product of V, V was, I see it up here. V is minus 2, 1. So let me just put it here. V is, so we don't have to keep scrolling up. All right. So V dot that is minus 2 plus 3. So it's 1. Okay. So I get 1/5 times minus 2, 1. Okay. And we see that that is what we obtained there. So there we go. And then let's do the second one. So perp V of 1, 3 is going to be 1, 3 minus 1/5, right? The projection minus that. Okay. Which is going to be, if you do the algebra, 1/5, 7, and 14, which is what we got. Okay. So that's just a confirmation that the standard matrix is doing what it's supposed to do. It's supposed to give you the correct output for whatever input you plug in. Okay, and you can see this is going to work for every matrix. Good. So that's an example of computing the standard matrices, but the crucial step is to recognize that the function you're trying to compute the standard matrix for is a linear mapping. Okay, otherwise the matrix you come up with won't have much to do with the function. All right, so the next important topic, following typically what we do in calculus when we talk about functions, is composition. So it's the same terminology as in calculus. You have two functions. So here they are. So T1, T2, so mapping. So from some Rn to another Rk, we call it, and T2. Now notice the dimensions here are aligning. Okay, so these are the same. So you might not see that, it's pretty small, but the T1's codomain is the T2's domain. Okay, and the reason it's like that is because that's the way composition works. So remember, composition is ordered. So we're going T2 with T1. So the T1 is on the right, T2 is on the left. So there's the definition, as in calculus, same as calculus, same idea of composition. And even in calculus, order mattered, didn't it? So you act on a vector first with T1, and then you act on it with that output with T2. Okay, so the input must be the input of T1, which is Rn. Okay, so that's why the domain of the composition is Rn. It's the domain of T1, because T1 is the first thing you apply. Then you apply T2 to the output of T1. So the codomain of T1 must be the domain of T2. Okay, so that hence, that's why the Rk is here. That's the codomain of T1. It must be the domain of R2. So it's very important that these numbers align. The N and the M you see on the ends, they can be whatever, but these two must match, okay, because I need that for the definition. Good. So that's composition as in calculus. Now, of course, you're wondering, okay, fine. So we can create new functions, new transformations given two transformations. But is it a linear transformation? Because we, like I said, those are the important transformations for us. So that's an important fact we want to establish, that composition is a linear transformation. So let's go. So the proof is the following. So let's start with, I'm going to do the two-step properties of linear transformation, the vector addition part and the scalar multiplication. So I'll do it in two steps. So I'll take my composition acting on a sum. Okay, so here's my sum. All right, so I want to show, okay, I'll just put it over here again. I want to show that this ends up to be T2 circle T1 x1 plus T2 composed with T1 y. Okay, that's what I want to show if this composition is linear. So this particular output should be that sum on the right. All right, so I know where I'm going, but how do we get there? Well, first thing we do is I use the definition of composition. So this is actually T2 acting on T1 x1 x plus y. All right, so this is definition of composition. Definition of composition. Okay, and I'm going to give myself a little bit more room. Now, what I do with the argument there, the T1 acting on x plus y, is I use linearity of T1. Remember, I want to use all the properties that I see here. And that's not a 2, that's a 1 here. Okay, T1 of y. Okay, so now I used a linearity of T1. Okay. And then I'm going to use the linearity of T2, right? So there's a sum in its argument. So it's T2 acting on T1 x plus T2 acting on T1 of y. Okay, so now that's linearity of T2. Okay, and now I rewrite this as, because this is where I want to establish, this is actually the same as the composition T2 with T1 acting on x and the composition T2 with T1 acting on y. Okay, so that's where I wanted to go. And then for the scalar multiplication, let's do it here. So I start off with my function, which is this composition, acting on a scalar multiple of a vector. Okay. Then I use the definition of composition, which means T2 acts on T1 of Cx. And then I use the linearity of T1, so that's C times T1 of x. And then I use the linearity of T2. Okay, so the C's all the way out now, T2 acting on T1 of x. And then I recognize this as T2 composed with T1 acting on x, okay, which is where I wanted to go. Okay, so it is linear under scalar multiplication too. Okay, so important property then is, what is the standard matrix of a composition? How is it related to the two vectors, the two standard matrices? All right, so it must have a standard matrix. Okay, so let's go. Let's do it this way. Let's find out what it is. This is theorem, by the way, 3.2.5. Okay. So I want to write this as good. So let's go. Let's compute the standard matrix. T2, T1, acting on the standard, the ith standard vector. Okay, so I'm using the formula, the definition, I mean, of the standard matrix. So we've established that T2 composed of T1 is a linear mapping. It's a linear transformation. Therefore, it has a standard matrix. Okay. I should put it right here, maybe just some terminology here. This T1 box is this matrix A, and over here, the standard matrix box T2 is this matrix B. Okay, so you recognize that. They just happen to be calling it A and B here. I want to compute the standard matrix of the composition now. Okay, so I don't see that here yet. I see the standard matrices for T1 and T2, but not for the composition. So let's compute that. So this is the way we compute the standard matrix of any linear transformation. Okay, so there it is. Now, what is that? What is that vector then? Well, first of all, it's a composition. So it's T2 acting on T1, EI. Okay, not square bracket. All right, so now this is the first column of A. Okay, A given there. So this is T2 acting on A1, AI. AI is the ith column. Okay, so I'm using that property that if a matrix acts on one of the standard vectors, you get the ith column of A. Okay, so that's something you've seen before. I'm using that here. Okay, so just check that's a true fact. So that's why I'm writing AI here, A sub I to be the ith column. And now this is going to be, now T2 acting on AI is the same as B acting on this column vector, right? Because that B is the matrix, the standard matrix of T2. Okay, so that's the ith column. This is the ith column of the standard matrix. So this we see as the ith column of the product of AB. Sorry, BA, right? Order matters. Order, sorry, T2, yeah, T2 times B1, sorry. That's right, so I'm just making sure I got my matrices in the right order. Yeah, that's correct, okay. So this is the ith column of the matrix product, BA. Okay, and that's something that's also mentioned in the book, that when you multiply two matrices together, the columns of the product are going to be the products of the left matrix B, in this case, acting on the columns of the matrix on the right. Okay, so we've determined that the standard matrix, i.e. the standard matrix of the composition, is the matrix product, BA. Okay, so i.e., if you want to write it differently, so yeah, T2, the standard matrix here, is the product of the matrices, of their standard matrices. Okay. Now, so these are both the same, but here I don't have to relabel the standard matrices with A and B. So that's a very interesting formula. This is the reason, should I say it's the reason, but this is the origin, or why matrix multiplication is that kind of complicated formula. So of the way matrix multiplication is defined. Okay, you might have wondered why that kind of complicated way to multiply matrices was invented. Definition. Okay. Remember, when you multiply matrices, you're taking dot products of rows of the matrix on the left with columns of the matrix on the right. Okay, so it's that kind of complicated product. But that product works. So based on that product, we find that composition of linear transformations corresponds to matrix multiplication. If you had a different rule of matrix multiplication, then this theorem there wouldn't be a theorem like this. Okay, so we need that kind of rule for matrix multiplication so that we have this kind of theorem, that matrix multiplication is corresponding to composition of functions. Okay, so that's something you can get out of this theorem here. Okay, so let's move on to, so that's the theorem, I believe. Let me just see where I am. Yes. Good, so that's this one right here, okay? Good. So we've established that, and that's the formula I mentioned. So this is an example to just to verify that idea. So T omega is a rotation about the origin. So this is an R2 rotation. So that's a linear transformation. So this is a good example for you to think about. So here's my, I'm just going to make a sketch here. So there's my E1, and there's my E2. Maybe not so long, right? Actually, let's do it this way. Actually, I should make this a little bit bigger because I'm going to need, I'll just want to demonstrate to you that what is the matrix for the rotation again. So there's E1, there's an E2. All right, so we're doing rotations by an angle omega. So just like in calculus, when we rotate around the origin, it's a counterclockwise rotation. Okay, so we're moving, and maybe I'll put it into, I'll just put it into blue again. So I'm going to rotate the E1, and that's not my angle. This is my angle. Let's do it that way. Omega. So there's my rotation of E1. Okay, so this is T omega E1. So it's rotated E1 by omega, and also E2 gets rotated. Okay, so I'm assuming that the angle is positive. Okay, so now you can compute that these two components here, like this point right here, is the, yeah, I'll do it this way. So that point right there has coordinates cos theta. Okay, you can see that from the small diagram here, but there's a better diagram in the book. So when I rotate the unit vector, so E1 as length 1, I rotate it by omega. The point that it ends up at has coordinates cos theta sine, and that's not a theta now because I'm using this other symbol, which is omega. Okay. And then this point over here where it points, the E2 points to, has coordinates minus sine omega and cosine omega. Okay, so you can just draw those diagrams and you can see what they are. And hence, the standard matrix for that kind of rotation is going to be columns cosine omega, sine omega, and then minus sine omega, cosine omega. All right, so that establishes the standard matrix of this rotation. Okay, so easy to remember. TE1, first column, TE2 for the second column. What I didn't do here is show that rotation is linear. Okay, and you can think about that, right? Just geometrically, why is it linear? Okay, so you have to I didn't prove it, but you can imagine why that's true here. Okay, so let's do this two ways. So this is a composition of those two transformations. So we know already that when I compose two rotations, so rotation by alpha by rotation and then rotation beta, I'm just doing a complete rotation of alpha plus beta. Okay, so we know that. We know this. Okay, if I rotate first by alpha, then by beta, it's the same as rotating all at once, alpha and beta. So I already know what the standard matrix of the composition should be. Okay, it should be the standard matrix of this one, alpha plus beta, which according to my formula over there is going to be cosine alpha plus beta sine alpha plus beta minus sine alpha plus beta and cosine alpha plus beta. All right, so I know the answer. Okay, but let's do it now according to the theorem above, this one right here. Okay, so by theorem above, okay, this standard matrix would be the product of the two standard matrices. All right, okay, so let's do that one. Let's do it this way now, and we'll see that it does agree. Okay, so we have, so let's just do it then. So T beta, okay, I'm just writing it out, cosine of this angle beta, sine of this angle beta, minus sine of beta, cos of beta. Okay, and then T alpha is going to be same pattern, but angles alpha now. Okay. Good, good, good. And then, so let's do the matrix multiplication. So I'm going to get cos beta, cos alpha. Sorry, cos beta, cos alpha. Yeah. And then minus sine beta, sine alpha. Okay, that's my first component. Top corner. And then the second component in the first column is going to be sine of beta, cos of alpha, plus sine of beta, sine of alpha. Okay, so that's my first column of the product. Second column is going to be minus cos beta sine alpha minus sine beta cos alpha. And then the bottom component in the second column is going to be minus sine beta sine alpha plus cos beta cos alpha. Okay. And now I use these trig identities. Okay, trig identities. So sine of alpha, and you can look these up. Which ones do I need? Sine of alpha, cos beta plus cos alpha. Cos beta is sine of alpha plus beta. Okay, that's one. And then we have cos alpha, cos beta minus sine alpha, sine beta equals cosine alpha plus beta. All right, because I see those terms in here. Okay, so now I get the first one is cos. The first term in top entry, the 1 entry is cos alpha plus beta. I recognize that. And then the second term in the first column is going to be the sine alpha plus beta. And then going over to the second column at the top, I see minus sine alpha plus beta. And then once again, I see cosine alpha plus beta. Good. So we did show that, hence, the product T beta, T alpha. So I just, using the theorem, right? So I used the theorem and I verified the correct answer. The correct answer should be the rotation by beta plus alpha. It should be that, all right? Because we already know what the answer is, okay? So the theorem is just confirming that the theorem is correct in this example. Okay, now something more challenging is this example here, which is a reflection across a line. So let me draw a picture of what we mean here. All right, so there's R2. There's a line, okay, the line L. Okay, what is reflection across this line? Well, you take a point X and then you reflect it across a line. So think of this line as a mirror. So you move toward the line L so that your line of sight is perpendicular. Then you move the same distance on the other side as you are. That's the image. So let's call it X prime. That's the image. Okay, so X prime, according to this way this question is worded, is going to be the image of X under this reflection. So read this question. This is the angle omega right here. Okay. Now, if you think about it, that is also a linear transformation. Okay, so our goal is to compute the standard matrix. Okay, and I'm going to do it this way. This is also on page 189 of the text. Okay, and they derive a formula. Okay, so they're talking about the same thing here. So reflection, this is their notation of a slope of a line with normal n though. Okay, so this is a different kind of formula for it. It's going to be x minus 2 times the projection along the normal. Okay, so this is in the text. Okay, so the normal vector is going to be this vector right here. So it's normal to the line. And you can see why that's true, because when you project x onto n, you get these two, I'll put them in green, okay? You get these two components right here, okay? So this is actually that vector right here, okay? So I'll write it here. This is projection onto n of x. There it is, right there, okay? And actually, I probably drew it the wrong way. Let's see, x. Yeah, I drew it the wrong way, sorry. So let me do it. Let me just, the head's going the other way. That's what's wrong. My diagram I just sketched here is in a different order than in the book. So it goes that way. So that's why you start at x and you subtract 2 times of these to get to x prime. Okay, so that's what's done in the book. Okay, but that's not the standard matrix. So let's compute the standard matrix, but I want to use composition. So here it is. So this TW, I'm going to write it as a composition of 3 transformations. Okay, so the first one you do, which is the one you put on the right, is rotation by minus W. So R of alpha is rotation by alpha. So that's my notation here because T's been taken up by this question using it for the reflection. So rotation by alpha. And this is what we just finished doing above, okay? It's above. So rotation by minus omega. So what that means is I want to determine, given an x, what is x prime? All right. So first I rotate everything down by minus omega. So the L lies along the, maybe I should write that down here. So now line L lies along x-axis. Okay. Right. So if I rotate by minus omega, everything goes clockwise by omega. And in particular, that line ends up lying along the x-axis. Good. Now I do the reflection. Okay, so this is the next transformation, and I'll call it Rx. All right. So Rx here is reflection, because this one is an easy one to do. Reflection across x-axis. Okay, so now I'm doing the reflection after I've done that rotation by minus omega. And so I do this because I know I've already written down what the standard matrices are for the rotations. What's the standard matrix for this reflection? It's easy to see that it's simply 1, 0, 0, minus 1, i.e. you have this vector x, y. If I reflect it across the x-axis, it goes to x minus y. You knew that, okay? So that's the matrix for it. So I do the reflection, and then I rotate everything back up counterclockwise by omega back to where it started. So now I do this. Okay, so that's, now you might think this is a complicated thing to do, but this is absolutely very standard procedure in computer graphics. You're putting together transformations. This is actually a complicated, we'll see the matrix for this supposedly simple transformation reflecting x across a line is actually quite a complicated matrix. Okay, you won't be able to guess it. So this is one way to unravel those complicated transformations, reflections around oblique lines and such things into simpler ones. So I can do reflections pretty easily across the standard axes, okay, the simple matrices. And I know rotations now too. So let's do this. So the standard matrix of this T, according to the theorem above, is going to be a product of these three matrices. Don't mess up the order. Okay, that's important. All right, so it's going to be that. All right, so let me just write it out once, and because it's getting kind of late here, I'll just I'll give you the answer. You guys do the calculation. So the matrix on the left here, rotation by omega. Okay, so that's these matrices. Okay, so those are the ones you remember. Okay, fine. And then you have this rotation or this reflection, the easy one. Then you have another rotation by minus omega. Okay, now I'm not going to write cosine of minus omega or sine of minus omega. I'm just going to use the odd and evenness of the function. So cosine is even. So the cosine of minus omega is cosine omega. Sine is odd. So sine of minus omega is minus sine omega. So there's two minus signs there. So I get sine omega. But on the bottom, I get minus sine omega. Okay, and then cos omega. So I skipped a step here. I should have written cos of minus omega, sine of minus omega. I should have, but I did it in my head, and I used the oddness and evenness. Okay, now I'll just go through this quickly because I've done it before. So I have to multiply three matrices together because I know you're dying to see what the answer is. So this one, if I multiply this matrix together, I get, I mean, this is not hard, right? So cosine omega, sine omega, right? And then I get sine omega minus cosine omega. All right, that's those two. And now I do these two. Okay, so let's do those two. Well, I'll just give you the answer. So I get cosine squared omega minus sine squared omega. That's the first term. And I get sine omega cos omega. I get two of those, so I'll just write it out here. And then I also get two of those. Maybe it's the NAD or it doesn't matter the order. Okay, depends how you want to multiply them. So 2 times the product, and then I get sine squared omega minus cos squared. So you guys verify that. Okay, this is what you get. And now I'm using trig identities to simplify this. Okay, and the ones I use is 2 times cos alpha sine alpha is sine 2 alpha, and cosine squared alpha minus sine squared alpha. These are the expressions I see there. Cos 2 alpha. All right. So my standard matrix for this kind of reflection is cosine. So omega is the angle of the line. So 2 omega sine 2 omega sine 2 omega minus cos 2 omega. Okay, so for a line that's rotated by omega, this is the standard matrix. So let's just check. I mean, do we believe this? Okay, so for example, if I take the diagonal line, all right, so this is the omega is pi over 4, okay? I think you know that if you take the point with coordinates x, y, and you reflect across the diagonal, you get the point with coordinates y, x, okay? You can prove that geometrically, all right? So what is this matrix here? This matrix that does this operation is 0, 1. It interchanges the order, right? This is it. So let's check that our rotation matrix does that. So T, according to our formula, pi over 4, and you can do it for other angles that you can easily see how the reflection works, is, so plug it in. So if omega is pi over 4, 2 omega is pi over 2. Okay, so that means cosine of pi over 2 is 0. Sine of pi over 2 is 1, and I get 0. Okay, so it is correct. All right, so that's for this problem of reflecting across a skewed line, this oblique line, you have a formula like this in the book. Okay, that's one, but that's not a matrix formula. Okay, it's the same formula and it gives you the same answer. But if you wanted to implement this on a computer with computer graphics, you're going to all your transformations are going to be realized by the matrix multiplication on the computer. Okay, so that's a good example, I think, of how to use composition to compute the standard matrices of more involved geometric transformations. There's many geometric transformations that are rather complicated, even to visualize, but you can break them down into simpler geometric transformations. So the geometric transformations are the ones that are discussed in the next section, rotations and reflections and projections. Okay, those are the standard basic geometric transformations, but from those, by composition, you can obtain a much larger group of geometric transformations, like this one right here, reflections across oblique lines. Okay, so I think I'm done now. Thanks for your attention. Let us stop for the day.